Yeah. Thanks. Okay, let's start.
Yep.
Nice.
Excuse
Yeah, hey, thanks.
Physics.
Yep.
Good. I need to go through most of the topics.
No problem. I think we're gonna go through all.
Yeah.
Before the school start, okay, let's learn as much as you can. Chemistry. Okay.
We start from kinematics.
Okay, yeah.
Or,
Yep, sure.
Yeah. Need paper and start.
Yeah. Cool. Okay, kinematic, let's start with something called the definition of them. Okay, so this is called, I cannot read the words. That's bad, man. Must I use a laptop? Okay, anyway, it is called, you understand what's displacement?
Yeah.
Versus distance?
Yeah, displacement is with reference to the origin.
Reference to origin is the shortest line. Displacement is an arrow, okay? Just think as an arrow, have length and have the. So can I say the displacement is the length is negative?
Displacement negative can for displacement.
Okay, if it's displacement negative means what? The negative means is the length is lesser than 0 or the direction is different.
The direction is different.
So can I have the length lesser than 0 or not?
No.
For any vector you cannot have a length lesser than 0. Okay, scalar you can have a number lesser than 0. Okay, so this is a displacement. And velocity is the speed in a specific direction. Okay, speed, you know what is speed? Okay, can the speed be negative?
Speed cannot.
Yeah, velocity can be negative, right?
Yeah.
So acceleration, scale acceleration is the rate of change or rate of change of speed or rate of change of velocity. Okay, actually it should be defined as rate of change of velocity. Okay, because the there is a change of either speed or the direction. You also have acceleration. Okay, average velocity, take the average. Take the total displacement divided by time taken. Average speed, you just use the total distance traveled divided by time taken. Okay, whatever it is. Okay, so just like that, displacement. Okay, I think we can cut these things. Okay, now this is not a very good example because you can see a parabola. Okay, but what they're interested in is only the up down motions. Okay, so they're talking about the up down, but it's very hard to visualize or draw things in up down, so they draw a parabola. Okay, but let's just talk about the up down motion. So the idea is that you have one dimension kinematic. Okay, so the kinematic one line, some graph representations. Graph we have two kind of graph. One is the displacement time graph, and another is the velocity time graph. There is a distance time graph and speed time graph also. Just adjust that accordingly. Okay, so it is a vector.
Yeah.
Okay, vector over a scalar is still a vector. Okay, if it's scalar over scalar is another scalar. For example, I have a vector A. Okay, divide by 2, scalar, right? 2 is a scalar, right? Vector A in max. Okay,
Yeah.
go back to max. Okay, so it becomes half A. Okay,
Yeah.
got it? So it's still a vector.
Yeah.
Okay, but if you say that 4 is a number, okay, number divided by 2, okay, is still a scalar. Okay, scalar divided by scalar is a scalar. Vector divided by scalar is still a scalar. Okay, so it's still a vector. Okay, so long as this is velocity, if this is the displacement, time, maybe the gradient, which is divide, or the area, which is multiply. Okay, why was it multiply? Because last time you count boxes, right?
Yeah.
Count boxes is actually you find the areas of everything. Find the areas of everything. Actually, you are using the height and width of all the small boxes. So it is actually multiplications. So if this is a vector and a scalar, the gradient will be a vector. The area in the graph is also a vector. Nothing changed, right? Okay? Either scalar, dy, or time is still scalar. Okay?
Yeah.
Secondly, so if you talk about gradient, right, you can play around with the unit, okay? If it's a gradient, you just use the unit divided by the unit. So it is a meter per second, the gradient is kind of thing in meter per second, so you know it is kind of things like velocity. Okay?
Yeah.
So this is a meter per second, divided by second, you got meter per second squared. So this is why in the VT graph, you know this kind of things like accelerations. Okay? In the area under graph, which is multiplication. Multiplication, if you use a meter times second, meter second, which is a momentum, so which is a bit different, which is not this chapter, okay? Next chapter, you have impulse, then you talk about momentum. Now, but in this graph, you have a meter per second times second, right? The area under graph actually gives you the meter, which is a displacement. Okay?
Yeah.
So just play on the unit, you know what it is. Okay. Now, so let's talk about, so all this graph, right, we'll handle them in MCQ, okay? Just need to practice a bit, but except for the time you should practice until you're sick already. Let's talk about displacement, velocity, and accelerations. Now, they're all vectors. Vectors have directions and the components, and the length, okay? Length-wise, no issue, because the displacement, the length is the distance between 2 points, okay? Okay, the shortest distance, but still counting a distance, easy understood. Velocity also, if you talk about the length of velocity vector, okay, which is like speed, so fast, slow can tell you already, okay. Accelerations, okay, the length is just accelerations or the increase in speed, how fast they increase the speed, how fast they retard the speed, those things, okay, the speed of the speed. Okay, okay. So the only issue is the directions. Okay.
Yeah.
What is the direction of a displacement? Direction of displacement is still very simple. Okay. Direction of displacement, draw the first point to that point. There's a direction of displacement. For example, if I have an object, okay, being thrown in this way, okay. So let's don't talk about the whole situation. Let's talk about until here. Okay. At this instant, you start from here. Okay? At this instant, okay. At this instant, what is the displacement? Okay, displacement. Then you stick to your definitions and throw away all your emotion, throw away all your feelings. First point until this point, draw a line with an arrow. This is displacement. So this length is a displacement length, and direction is these directions. Okay. So interestingly, right, at the instant you are heading this way, but not this way. Okay.
Yeah.
So the idea is the direction of displacement is never a direction of, or most of the time it's not the direction of the motions where you are heading at the instant. No. Okay. So this, what direction is that? Okay. This direction is actually the direction of the motion. Okay, which is direction of velocity. Okay. So we know the velocity. Okay, velocity. The length, right, is actually speed.
Yeah.
Okay, the direction actually is the direction of motions. So you want to know exactly where it is heading at the instant is the direction of velocity, not acceleration, not displacement. Okay, so displacement direction no issue, velocity direction no issue. So what's the direction of accelerations? Direction of accelerations, right, at this instant is downward. Why? Because it's the acceleration come from mg. Okay, which is 9.1 downward. Okay, through the whole motion. It's projectile motions. Okay, so therefore, right, direction of acceleration. How do you determine? Is the direction of the resultant force. Okay, this is very important. Direction of accelerations is direction of the resultant force. Not any component, but the resultant force. Okay.
Again, the direction.
Direction of acceleration is the direction of the resultant force because F equals ma. And this F is not any component F, which is the resultant force. So this is the scalar, this is the vector. So it's like 2 times if a 2 times vector B equal to vector C, that kind of things, you know the B directions got to follow the C's directions. Okay? So kind of things like here this is a vector, so you know the direction of acceleration got to be equal to the direction of the resultant force. So whenever you want to draw accelerations, you need to draw the direction of the resultant force. Then you quickly got to think about what are the component forces you can have in your syllabus. Then you calculate the resultant force, you get the resultant force value and the direction of resultant force. Okay? That's how you get acceleration. So remember, what are the causes? It is the forces cause you summarize them, So sum it up in a vector way, add it up in a vector way, it will give you the resultant force. And it is the resultant force that will give you the accelerations. It is the accelerations that will give you the change in speed, velocity. Okay? So when you find accelerations, the time you've got to ask yourself, who is the fellow create accelerations, which is the resultant force, not the change in speed. Change in speed is a result of accelerations. Okay? So look whether you can find any resultant force first. Okay? If yes, go to use them to find accelerations. Else, go to see any change in velocity that you can show you the accelerations, that's still fine. Okay? So now this is some the four things: the forces, velocity, accelerations, and displacement. You got to get it very clear. So the second thing is we're going to teach you. You need some basic vector things. Okay. Whenever I say now this is very important. It applies on all physics vector. Okay. A resultant vector is always equal to summing up all the vectors. Okay. Add it up all the vectors. Okay. Or F1, F2. Or vector 1, vector 2, vector 3, vector 4. They add, but they add in a vector way. Okay? So, if you talk about this, that's ridiculously, that's called sum of velocity, okay? Sum of displacement, which is sum, then you have a sum of speed, or sum of whatever, or the resultant speed, or the kind of resultant whatever. Okay? If it is a resultant anything, is always equal to anything add up. Okay. After that, ask yourself: is it vector or scalar? Okay. If it is scalar, numerically add it up. If it is vector, do in a vector additions.
You mean you have to assign like a certain direction if you
No. Okay. So, if it is a vector, remember if it is scalar, you just add it up numerically. Okay. If it's a vector, you will tell yourself that I got to add up the vector in the vector way. How to add a vector in vector way? There's two ways. Okay. The first way, okay, is to combine the vectors and then draw the resultant vectors. The resultant vector will be the sum of all small vectors. Okay. The second way to do the vector summation is depends on whether it is okay. Let's say have two. Let's have 2.1. Okay. 2.1. Okay. Now 2.1 tells you what is the one dimension. Okay. It's one dimension is easy. Okay. So vector A, vector B, vector C. Sum it up, we just need to draw A, B, and C. Okay. In the number wise, right, if this length equal to 3, this length equal to this length equal to 1, you just need to say summation of all the forces is 3 plus 2 minus 1. Okay? Minus because you take right hand side is positive. So your answer is positive or negative tells you that the answer is positive or negative tells you the direction. Okay? It never tells you the actual value. Okay? It depends on where you assume to be positive first.
So do we, like, before your question, need to state the point where we assume that we take which direction positive?
Yeah. Okay. So, and secondly, right, you're not subtracting, right? Okay, you're actually adding, because what is called resultant. Resultant means all add, but if you add in opposite directions, it become add a minus value, so become a subtract. So you never subtracting, you always adding. Okay. Now, if it is two dimensions, which you will learn more in projectile motions, the strategy is exactly as what you did in Sec 4. What do we do? In Sec 4, right? The first way is to draw in max. Okay, then you say this is the sum of vectors. Okay, so by drawing in scale. The second way is to in A max we did a vector like that A, but they give them a column vectors, right? 2, 3, and then we say a vector B. Okay, say 1, 2, that kind of things. Okay. Then I say what's A plus B, or where A plus B means 2, 3 plus 1, 2. So therefore it's 3, 5. But what is this A plus B actually? It's actually you shift the B here and this is A plus B. Right? You did that without knowing actually you're doing it. Okay? So what does that mean? This is harder, this is easy. The idea is that you split the you split the A, okay, into 2 and 3, and you split the B into 1 and 2, 1i and 2j, and then you do a vector components y 2 plus 1, and then 3 plus 2. Then will give you 3, 5. Okay, so therefore you have 3, 5 here. Okay, now just to get you the feeling, you can forget about it. Okay, so what exactly we were doing is that if you have two vectors or more than two vectors, many vectors, you want to add it up. Okay, what do we need to do is that we first break them down. Any vector come out. Okay, we break them down to two components. And other vectors come in, we break them down to two components. Okay? And then we realize, right, the components will do business with the components. And the components will do business with components separately. So you get a resultant component 1. And this 2 can give you the resultant component 2. So from these two resultant, you'll be able to draw the actual resultant.
That means you are supposed to draw, you cannot use Pythagoras to...
You have to use Pythagoras theorem, right? If I find out this is 2, 4, that kind of things, you will say that, oh, the answer here is 2 squared plus 4 squared, that kind of things, right? You still got to do it, okay? Now, what I want to say is that the strategy of doing calculation method in any vector sum or any vector calculation 2 dimensions, you do this. In a 2-dimensional questions, you break them down to 2 times 1-dimensional issue. Okay, and then you do your calculations. Okay, then you got 1 dimension's answer. Okay, then with these two, right, you'll be able to come out the final resultants. Okay, so the idea is that how to do 2 dimensions, we only, human being, for us, we only deal with 1 dimension calculations. So the idea is to break them in 2, do each dimension's business separately, get the 1-dimension answer, then we combine them back. Okay, so what are the key things that which helps you to do a lot of these calculations? So first thing is this. Okay, to understand that if anything is the hypotenuse, right, of a vector, if you have an angle in this way, theta, opposite to the theta, okay, it will always be h sine theta. And adjacent to it will always be h cosine theta, the length. Okay? So this is how we simply break it down. Just remember the opposite one is sine. Adjacent one will be cosine. Okay? So this is one of the handy things. Secondly, of course, Pythagoras theorem, if you have A, B, okay, B, you have A squared plus B squared square root. Okay? Then you get back the Pythagoras theorem, and you know the angle is equal to inverse tangent of B over A. Okay, so these two are very handy. Now, so when do you use this? When I have 2 dimension, this is the way to break them down to each one's the 1 dimension. Okay, and you break all of them. Okay, if you have the displacement, okay, later we have an initial velocity, and then you have the acceleration in different way. So the accelerations, velocity do business with that displacement. This acceleration, velocity do business with that displacement. After a certain time, they all change to the final speed. Okay, so vertically final velocity, horizontally final velocity. Use back this one to combine back and give you the resultant. But that's always the strategy. Okay, just to know this strategy. Okay, for all the forces and all the kinematic also. Okay, so let's come back to the core things about the kinematic things here. Is that you need to remember there are how many variables there? There are 5 variables. Okay, 5 variables, which is S, U, V, A, T. Okay, S, U, V, A, T. Okay, displacement we use S. Okay, periodically, okay, you use S. This is initial velocity. This is final velocity. Okay, initial velocity and final velocity. Acceleration and time. Okay, only time is scalar. The rest are all vectors. Okay, the point is that if you have 5 variables, each equation will only involve 4 variables. Okay, each equation you learn. So totally you need 4 equations to cover all 5. Okay, whatever it is. Okay, let's just go through this. The first equation is x equal to ut plus half at squared. The second equation is that v squared equal to u squared plus 2as. The third equation is very simple one. Okay, I remember this way. Okay? Acceleration equal to final minus initial velocity over time. Change in velocity over time. Okay, but people will remember it's v equal to u plus at.
You manipulate them with.
Yeah. Okay, but this one lost the meaning. Is it? Don't know where it's from. Okay, v equal to u plus at. But actually, it's acceleration will change in velocity for every time. Okay. The fourth one, right? What I remember is the average speed or average velocity, which is displacement over time, which is also equal to v plus u half. So you got to remember this.
What is it v plus u half?
Now v means final speed, u means initial speed. If it is a constant acceleration, the average value will just be the v point. Got it? Okay.
Yeah.
Now when do you need to use these four things? When acceleration is a constant but not zero. Okay. So what if acceleration equals 0? When acceleration is 0, you only have one equation, which is speed equal to distance over time. Primary school things. Okay, don't think too much. When acceleration is a 0, you use this. When acceleration is a number, a certain value, you use 4 of them. Okay, but acceleration is a constant or a number which is not constant. Okay, you can only do by graphical method with all the integration and differentiation that you did in AMAX. Okay. Now, to analyze these 4 equations, you need to know these 4 equations, right? Each of them have 4 variables. So that means there is one variable missing from each equation.
Yeah.
So from here, you know that what is missing is that there's no v. Okay? Now in this case, there's no s. Sorry, nonsense. No t. Okay? In this case, right, you have no s. Okay? This one has no a. Okay? So the idea is that there is one stage, right, which is not allowed or it cannot do in all these equations, is the no u. So how to handle when your case has no u? Okay, all you need to do is to take any 2 equations, 2 simultaneous. Okay, you take 2 equations, there's no u. Okay, so your answer, the answer that you want is one variable. But in all these things, right, you can't find u. Okay, so most probably you need the answer u and answer u come with 2 equations, okay, and do a simultaneous equations, or use your GC to cut the 2 points to find answer. Got it? Okay, so 4 is sufficient to cover all. So in case no u, you do simultaneous. But so far, if I see most of the question will not be so mean. Most of the time is no one of them. Okay. So good. So how to handle a question using all these things?
Which questions are right?
Yeah, but now it's still 1 dimension only. We'll come with the 2 dimension things. Okay, wait, okay. Let's do a simple one first, okay? Right. Let me finish everything. Okay. I want you to do things like in a very systematic way without much thinking. 10 questions come, 10 questions can be done this way. Okay. So when you have an object, can initially throw upward with initial speed of 2 seconds, that kind of things. Okay. What if this is cliff, right? Let's say 10 meter like that. Okay. Take G as for the sake of simple calculations, take G as 10. Okay. You can use 9.81. Okay. So what is the speed when the instant that it is about to touch the ground? Okay? Okay? So
This one
yep.
don't need use parabola.
No need, because it's vertical up down.
Oh.
Okay? Vertical up down. Okay? It's 1 dimension. Projectile that asks for range, you can do that. So very simple. Now first list out, okay, S U V A T. Okay, so filling one by one. Okay, now S is minus 10 because I'm going to take upward as positive. Okay, up to you. Okay, you can take down as positive. So S equal to minus 10, U is equal to 2, V is answer unknown, acceleration is equal to minus 10. Okay, T is I don't know T. Okay, so from here now, in order for you to form equations, you need your answer to be in the equation. Come on, okay, otherwise one will find. So and for any equation, you need to choose 4 variables. Okay, so the idea, of course, you choose these 4. Okay, so you choose something which is no T. Okay, so the second one is what you need to choose. Okay, in a systematic way, if you train yourself as a robot, 10 questions come, 10 questions to different, and substitute according to what you've written here. So V squared equal to U squared plus 2 minus 10 and minus 10. Okay, so equal to 4 plus 200, so 204, V equal to square root 204 meter per second downward. Okay. Another one, okay, just for the sake, okay, one more. I have same cliff, okay. I idiotically throw my object downward, and with say 4 meter per second, okay. And when time it reach here, right, okay, the time taken is equal to 4 seconds. And the speed when reaching the ground, it is actually 3, no, cannot be 3, we'll call it more. Okay, let's say 16 meters per second. Okay, so what's the height here? Okay, so again, now U equal to 4, S is what I need, SUVAT. I think I give a bit too much. You don't have to give me a final speed. Yep, you don't have to give me a final speed. V equal to V, I don't know. This is something unknown. Acceleration equal to 9.81 positive, and time is equal to 4 seconds. Okay, it's good enough. So choose 4, 1, and my answer here 3, 4. So you choose something which is no V. Okay, no V is this one. Okay, it's this one. So you use S equal to 4t plus half 9.81 of t squared. Okay. Calculate answer, you know the height of the whatever it is. Okay. Now, but before I say all this, right, in all the chapter, in all your physics questions, before you jump into each one like kinematic dynamic concepts, right, before that you always think about conservation energy. If conservation energy can solve the questions, you just use conservation energy to solve the questions. Okay. Now, when kind of conservation energy give you an answer, most of the time is involve a t time. Okay, conservation energy can only give you initial, final thing, everything about energy change, can never tell you the time. So it asks you for time, or you need to use time for as a reliable insight, and most of the time you can't use conservation energy. Okay, so if you can use conservation energy, like this case, you can. Okay, my initial KE initial is half m2 square. Okay, and then and the instant I come, and initial potential energy go to mgh, which is m10, h which is 10 meter. Okay, now KE have no direction, so you don't have to care about positive and negative. Okay, so when I instant when reach here, right, all the initial kinetic energy and all the potential energy, you should all be here as a point of a kinetic energy. So this should equal to half mv squared. So the m cancel, right? You know that the v now half this one times 2 will do. So v squared, right, is equal to 2 times 10 times 10 plus 4. Okay, you know it is equal to 204. So v equal to square root 204 straight away, so fast. Okay, so tell yourself wherever you can do a conservation energy, do it first. Okay, things like this, if you use the time, right, then you might not be able to get the conservation energy, because even though you get the final speed with that is not what we asked for the height.
But if you get the final speed, you can use acceleration v minus.
No, you still got to use the time. Acceleration 9.81. You still need to use the time to go to find out the height. Okay, so no point. Okay, now for example, in this case, I have 4 kilometers per second, so I have half mv squared. Okay, but the height is what I need, so it's mgh. I want to find my h, so my unknown is here, but I don't have a final speed. Okay, and they give you a time where you can derive it. What's the point? Use the kinematic. Okay, got it? Good. Now, one dimension things handle finish here. We go to 2 dimension. Okay, so how to handle any 2 dimension questions? Same idea. Okay, 10 question come, 10 question do it this way. Do by a method of tabulations. Now, if I have initial u with let's say 5, let's say this is 30 degree. Okay, you throw off to the cliff of let's say 10 meter. Okay, I want to say, well, what's the range then? Okay, range means horizontal distance to travel. Range. Okay, so you just drop it this way. Okay, don't have any ideas. Okay, so how do you do this? Very simple. All you need to do is to first list out do a table. Okay, S U V A T. Okay, now then you just add extra column here. Then you just say vertical. Okay, do a horizontally. You take right hand side as positive. You say vertically. I take up to you. Upward as positive if you want. Okay, now so we have all these things set. Fill everything. Okay, those you don't know, you still don't know. Okay, but a few things. What to fill first? Always acceleration first. Okay, because acceleration nothing to do with these questions. Okay.
Yeah.
Acceleration horizontally, we know there's no force in the horizontal direction, so acceleration equals 0. When acceleration equals 0, right, initial speed and final speed are the same thing, so you just need to fill any one box. Okay, they're the same thing. Okay, so when you have vertical, okay, you say that vertically you only experience one force in this case, which is the mg. Okay, so if you only have the W equal to the resultant force equal to W, so ma got to be equal to mg. So therefore acceleration only equal to g. Okay? So therefore acceleration here is upward positive, so put minus 9.81. Okay? Okay, then you fill in the rest with some sense. Okay? The horizontal distance is the range that I want. Okay? Vertical distance travel is minus 10. Okay? From first point to last point, vertically draw a vector, you know the vector direction is downward. Okay, so it's take upward, so it's minus 10. Okay, now horizontally you zoom in, you realize that it is 5 and this is 30. So if you break that up, this is 5 sine 30, this is 5 cosine 30. Okay, so horizontally the initial velocity is 5 cosine 30. This is 5 sine 30. Okay. Speed vertical I don't know, so I just put speed final speed vertical. Okay. Time t I also don't know when I reach here.
Yeah.
Okay. Now only when you reach here you can reach the 10 meter. Okay. Only when you reach here you can get the r. So that means the time taken, everything got to stick with this instant. So the v also stick to this instant. Okay. Whatever it is, okay, I'm interested in this answer. Okay. So in here the acceleration equal to 0. So what's the formula I have? Is cos speed equal to distance over time.
Yeah.
Okay, nothing else, right? It's too cheap. 30 equal to distance over time. Okay, so in order for me to calculate the r, I need to calculate the t. Yeah. Now remember, this 2 column, there's only one variable you can borrow from one another, which is the time. Because at the instance that vertically reach here is the same instance that the horizontally reach here. Okay, so only the time is the same. You can borrow in one another. So if you need this, you need this. If you need this, in this column, acceleration is a constant, so you choose 4. Choose 4, find t, get r. Okay, so what is this? No v. Right?
Yeah.
No v vertically means what?
S equals ut.
Yes, s equal to ut plus half at squared, right?
Yeah.
So s is minus 10 equal to u, which is 5 sine 30, while t, I got a quadratic, half minus 9.81 t squared. Okay. No sweat. Once you get this, how are you going to do?
GC.
Yeah, with the GC, right? Get the t first, put in the t there, multiply it, you get r. Okay, get whatever you want with this method, always list out and try. Okay, that's all for the one-dimension and two-dimension kinematic. Okay, all these things. Range. Now, okay, this is what we did in AMAX last time. Is everything don't have a number. So all these questions comes in and find out this kind of things, right?
Yeah.
Everything is number and symbol. Okay, so everything is generic. Okay, so they prove in this way. Okay, so they find out that it is like that. Okay, sine 2 theta. So when r is maximum, okay, now u square initial speed. Okay, let's say with the same speed, you keep changing the angle, which is the instant that you can have the biggest range. Control the biggest range. So you play around this function. If using the same speed, initial speed, this is fixed. G is fixed.
Yeah.
So you want a maximum of sine 2 theta. Sine function maximum is 1. So 2 theta got to equal to
45 degrees.
no, 2 theta got to equal to 90 degrees.
Yeah.
So theta equal to 45 degrees. Okay, but how do you prove this? It's very simple. If you look at it, very hard, right? Okay, so how to prove this? Use this. It's very simple. Now, horizontal ground in this way. This is a range R. Okay, come with this table. 3 column. Horizontally, right is positive. Vertically, up to you. Okay, up positive. Okay, S U V A T. Now everything is simple now. Very jialat. Okay, so what do you need to do is that initially I have a U, I have an angle theta. Okay, and that's all you need. Horizontally is a range. Vertically is 0.
Yeah.
Okay. U initially is horizontally is U cos theta. Acceleration is 0, so you don't bother about it. Okay, this is U sine theta. And velocity, final velocity, I don't know. Okay, actually should be the same, but just pretend that you don't know. Acceleration is minus g. Okay, g is the number 9.1, so minus g, because I think I was positive. Times t. Okay, everything is simple. So you want to find r, the range, right?
Find the t again.
You need to find this. You need the t. The t can borrow from here. You borrow from here. You need 4 of them. So obviously this one I don't want. Okay, so 1, 2, and 3, 4. Okay.
Same equation.
Yeah. Now, but good thing is that you have a 0 here. Okay. So without this is that s u ut plus half a t squared, right? S equal to u t plus half a, which is minus g, okay, t squared. Okay. A good thing is you have a 0, you can bring it over. You can bring it over.
Double positive already.
Yeah. Okay. So let's cancel the t. T not equal to 0. Okay. So you have gt equal to 2u sine theta. What I want to get t. Okay. So t equal to 2u sine theta over g. Okay. So at the left hand side here, you know speed, you distance over time, right? So speed equal to distance over time, and I'm interested in r, so r equal to u cosine theta t. Okay. So substitute with the t inside, you will have u cosine theta 2u sine theta over g. Okay. Therefore, you have u squared over g of 2 sine theta cosine theta. Therefore, you have u squared over g of sine 2 theta. Okay, so that's the proof. Okay, so no sweat. Once you come out this, nothing can be hide, and the only thing is that you can borrow about in here. But as what I say, okay, people get very tempted whenever they come to here. But you can always use the conservation energy. Okay, conservation energy. Now, there's one prohibited way of technique in the kinematic here. Okay, I'm going to teach you, but you should only use it in the MCQ so that nobody knows you're actually using it.
Okay.
Now, kinetic energy is scalar. All energy is scalar, right? It doesn't make sense 2 joules to the right, 3 joules to the left, right?
Yeah, yes.
But so this is why it's prohibited. When we talk about kinetic energy, Okay, I'm going to tell you this is mathematically possible to say this is horizontal kinetic energy, this is vertical kinetic energy, and in projectile motions, right, when it drops, right, the horizontal speed never change. So therefore, in a prohibited way, you're going to think that the horizontal kinetic energy never change. So the only thing changed is the vertical kinetic energy will become the potential energy and the new vertical kinetic energy. Wow, which is totally not allowed, okay? Remember, it's not allowed. But you can do it. Why? Reason is that if I have a V, okay, let's say we talk about horizontal component will be V cosine theta. Vertical component will be V sine theta. Okay? So we talk about energy as a whole, the kinetic energy is equal to half mv squared. Okay, if you have something called the horizontal kinetic energy, then right, the horizontal kinetic energy, which is not allowed, is equal to half mv cosine theta squared, which is half mv squared cosine square theta. And as you can see, the vertical accordingly will be v sine theta squared, which is half mv squared sine square theta. So the idea is that if you add the kinetic energy horizontally plus the kinetic energy vertically, you have half mv squared sine, cosine square theta plus sine square theta, which is equal back to half mv squared, because sine square cosine square equal to 1. So therefore equal to kinetic energy total. So this is a shocking truth that numerically, if you make it horizontal kinetic energy component, vertical kinetic energy component, you add them back. Why you just add in this way? You don't use Pythagoras theorem, it's a scalar one. Okay, it's a scalar, okay? So actually it's a scalar, but you still can think 50-50, like there is a horizontal amount and a vertical amount. They just divide in a numerical way because of this sine square cosine square equal to 1. Okay, so this can help you to cheat a bit. Okay, in case you have projectile motions, you need not to come to calculations. You straight away says the vertical kinetic energy component has changed by how much. So my final vertical kinetic energy is how much, and da 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 da. You got the answer.
But it can't be there in this way, right?
You can't do that in the long quack and short quack. Okay, come on, MCQ. You only have 40 seconds per questions, right? If you are master with all this, right, you can get you can do something that people may spend like 25 minutes to do it. Okay, now example. Okay, dangerous. Okay, so I tell you, don't let anyone know. Okay, if I have let's say 10 and I shoot 30 degrees up. Okay, now if I know this is going to be 10 meters, what is the final speed? What is the final speed here? Standard questions. Oh, final speed, right?
Yeah.
So as what I say, if you can do projectile motions in a projectile way, fine, okay. But as what I say, in all chapters, you should first think about conserving energy. There's no time elements here, right?
Yeah.
If I cheat, horizontal KE, this is a final KE, right? Final KE. KE equal to half mv squared, okay? Okay, so initially you have the KE.
MGH.
You have the this, right?
Yeah.
And then you have how can I just use the KE and change the MGH give the final KE? I can't. I don't know how to break down the components. Then you can straight away use this already. You don't have to do that if I ask the resultant. That's bad. Okay, so what it says that, what if they say I want to find the vertical velocity? Final. Okay, now if that's the case, vertical velocity, right? Talk about in energy, you must consider all. So that is a kinetic energy vertical, kinetic energy horizontal, and this is MGH, and this is kinetic energy horizontal and vertical. Okay.
Yeah.
So the idea is that horizontal kinetic energy component never change.
Okay.
It's the same amount because same V, same M, right? So therefore, it says that the KE of vertical initial plus the mgh you have is equal to k e vertical final. So half m 10 sine 30 square plus m 9.81 h, which is 10, okay, equal to half m v okay, square. Okay, cancel the m, okay, time 2, okay, take a square root, okay, done. Okay, so up to you, but even if you put it back, right, it's not that hard. Okay, so just some extra info for you to learn. You can just use this. Okay, now it's not just talking. Okay, so now is the time for you to show your understanding. Did I? There's some some more weird case here. If you have things bounce in this way, right? The idea is that it is we just don't know what happened during the impact of B, D, E, F, and H. Okay, we don't know what happened here, but we know what is right before and right after. Okay, okay. At A, it is fast or slow. Fast. From fast getting slower or slower getting faster.
No, I mean slower getting faster.
So A is fast or slow?
Slow.
Slow, okay. A, C, E, G, right, are all slow. At B, D, F, H are fast or slow? Fast, okay. So it's fast, okay. They are actually slow, okay. But the instance that when the object hit the table, the time is fast or slow? Fast. When the instant and why it bounce off the instant is fast or slow?
Should be fast or slow.
Should be fast or slow because later get slower. So that instant will be fast. So this is why, remember, right before B is fast, right after B is fast, they're all fast, and fast means high speed. But the direction of the motion is totally different, right?
Yeah.
So this is why you have a fast B before and fast B after. You gotta have some value, okay? So that it slowly go down again. Why is that? Oh, this is the wrong axis, yeah?
Yeah, wrong.
Okay, it's all wrong. Okay, so it gotta be this way, okay? So so therefore you have these 2 points, you don't know what happened in between. Okay, so just draw it, okay? So if you draw it, you know that in this instance it's very sharp and negative gradient. Okay? Slightly negative, but very high gradient. Right? So the acceleration at that instant could be a very negative high value. Okay, so that's why you have this point, you have this point. And for all this gradient, it's the same gradient. So this one acceleration is the same amount. Okay? So in displacement wise, you would take the initial point is 0 displacement, that means it's the displacement with respect to the initial point. Okay, so you start with 0. Wow, what happened to the graph shift? Start with 0 supposedly.
Yeah.
Okay. Then when you drop down the time, you'll have a greater displacement. Okay, far away from the original. So this is the vector. 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 Okay. So this is why the vector is getting larger, getting smaller. Okay, getting larger. Okay, until this point, getting smaller, getting larger, getting smaller, getting larger. And you know that this length and this length is the same. So that's why this length, and this length is the same. Okay, so this is why you have the displacement that way. Okay, the chase accordingly. Okay, the length short or long, the direction where you want to take positive. Where's the definition from here and there? You can plot all the critical points and see the pattern. And time you plot all the critical points, you don't know whether bend, then will tell yourself what is the gradient. Gradient means velocity. So is it getting faster? Yeah, the gradient can be sharper, right? So faster. Okay. So then you know curve in this way, curve in that way. Okay, good. Okay, so this is the first weird thing. The second weird thing is what if you have the air resistance? Okay. Oops. You have the air resistance, right? We need to know about the viscous force. Viscous force is proportional to velocity, and of course opposite to the motions. Okay, for laminar flow, is proportional to v squared if it is in turbulence flow. What is laminar flow and turbulence flow? Laminar turbulence flow is that when the airstream, right, cut the object, will give you some turbulence behind. Okay, so what happens is that you fly before? Airplane.
Yeah.
Yeah, now you fly airplane, so 747?
Huh?
Those normal 747 jet, right? Boeings, yeah. Where they go to?
New Zealand.
Oh, New Zealand, yep, certainly is that kind of plane, okay? So, what happens when they land? Got a lot of things, right? But when they start to land in time, you realize that the wing, the air flat, right, open up and push down, so a bit. But then they suddenly open another two small flat upward, which is against the normal downward things to suppress the thing. They suddenly open two pieces, very small pieces, upward. And once these two pieces go upward the time, right, okay, your whole plane shake like mad like that. That instant. But very short time, once it starts to shake, right, it stops already. Okay, can you remember that?
So now right at the end, it's very loud, then you
Yeah,
just come to a
but
loud.
once it's suddenly very loud, the time you just stop very fast.
Yeah.
Okay. Now that is when they change the laminar flow to the turbulent flow. Okay. The two small flat, once it's up, right, you create a lot of turbulence there. So the drag force to stop the whole thing here is proportional to velocity square. So suddenly velocity square then suppress the wave, where your velocity drop very fast and you straight will stop. But when turbulence force come in, right, you shake. Okay, you just shake. So that's turbulent flow, laminar flow. Whatever it is, it's like that. Okay. So what happened to the air resistance thing is that when you have object free fall but having air resistance, okay. Now the drag force is proportional to v. So let's say drag equal to kv. Okay. So your object is moving down the instance. So what is the resultant force? The resultant force equal to the downward force, which is equal to mg minus the kv, right? Always the case. Downward is mg, upward is kv, because you're dropping down.
Yeah.
Okay. But the idea is that in the beginning, in the beginnings, right, when time equals to 0, right, your velocity equals to 0. When velocity equals to 0, right, it means that your resultant force equal to mg. Therefore, you're falling A equal to g. But when A equal to g, right, it actually gives you an increase in velocity. When you increase the velocity, you got increase in drag force, because resultant force, but anyway, equal to mg minus kv. So v increase, okay, the whole product decrease, okay. Therefore, acceleration decrease.
Yeah.
When acceleration decrease the time, right, so long as your acceleration, if your acceleration is still positive, you will still have increase in v, but in a smaller amount. From increase in v become increase in v. Okay, but so long as your v still increase, right, you just have from increase in drag force become a further little increase in drag force. Okay, so therefore, okay, when acceleration is still greater than 0, this will still keep increasing, but increasing in a smaller and smaller and smaller amount. But you add it up, right? Okay, now the increasing in smaller amount, okay, sorry, the vector should be, okay, it still keep increasing. The velocity, can you see it? Because it's when acceleration greater than 0, your v is actually keep increasing, but the increased amount may be smaller. Okay, so the number is actually getting greater and greater. So long as these two are not balanced with one another, you will still have accelerations. Okay, you still have acceleration. You still have acceleration. You still keep increasing. So when you keep still increasing, right, you keep subtracting more and more. So the acceleration gets smaller. But so long as it's still bigger than 0, you still keep increasing. Acceleration is greater than 0.
Yeah.
It's keep increasing v. This is keep increasing. So it will feed back to this. So the whole thing will get smaller. But if this is still greater than 0, even a smaller amount, right, the v, it will still keep increasing. It is a smaller amount only. But the number is still increasing. Until what? Until the v value, right, kv will balance the mg. Okay? Then acceleration is 0. When acceleration is 0, your v will not change. So it stick to the same v, acceleration still sticks to the same 0. Same v, same 0, same v, same 0. So that's the terminal velocity you have. So what is the idea of terminal velocity? The idea of terminal velocity is that the terminal velocity will cause the kv or the drag force, right, balance the rest of the forces. Okay? Will balance the rest of the forces. So you need not to say that kv must equal to mg. It depends. What if I have another tangent or some other things? When it's not, the idea is that when it's not balanced, okay, you have resultant force. You have a resultant force, you have acceleration increase in speed, you will have a drag force. So the drag force, however it is, it will still keep increasing until it balances the rest of the force. That's how the drag force works. Okay. So this is why, right, when you have terminal velocity, okay, when you achieve terminal velocity at time, you will have your resultant force equal to 0. So mg minus kv equal to 0. And therefore, right, mg is equal to kv. Okay? Therefore, the terminal velocity will only depends on mg and k.
Yeah.
Okay? That means, right, the terminal velocity will not depend on anything like initial velocity, initial energy, how much you have, all these things. It won't care. Okay? So, let's say terminal velocity of mg over k equal to 20 meters per second. Okay? Let's say this time this divided by this equals 20. So Vt is 20 in that system. So what if you release your object from 0 meter per second? You keep dropping. It will reach 20 meter per second if it is long enough and forever there. But what if I throw my object downward, which is 40 meter per second? What do you think?
Does it drop 20?
You're right. That's what we see. Because it's independent. So this whole systems, right, will be on the other way around. Okay. So what happened here if you throw it down with 40 meter per second greater than the Vt? You have this one greater than mg.
Yeah.
The drag will greater than mg. So the drag will
try to decrease.
Will go upward. Will give you a decrease in v. Okay. So that it will still reach kv equal to mg. Okay. So the idea is that they will not bother. Okay. It will just depends on the system. How the kV balance the rest of the forces. Okay? So that's the air resistance. Now, some other things like this, okay, when a object is thrown up and then down, okay, you can do all this, but actually you can just observe one common sports, okay, that you certainly have done before. Now, if you say you throw a baseball, it's most parabolic, right?
Yeah.
Parabolic means there's no air resistance. The time up and time down most of the time is the same. So what can you have a big air resistance ball? The ball which will cause big air resistance, which is the badminton. Badminton behind the feather open up, right? Obviously, it is all for air resistance. So what happens when you hit the badminton in the parabolic path? The instance that you go to the top is fast or slow?
Slow.
Then the instant that you from top drop down is fast or slow?
Fast.
Fast, right? So it drops faster than you shoot it up, is it? The time taken I'm talking about.
I think
The time for it from your racket to the top compared to the top drop back to another player.
Drop back to up there faster.
It drop faster.
Yeah.
That means the badminton slowly go up and then come down.
Slower than the other. Slower than.
Or it is very fast up and then slower or come down.
That one.
Okay, do a very extreme case. Okay? Very extreme case. It is slowly go up and then come down, or It is go up and then come down. Which one seems to be more like badminton? Case 1, case 2. In your experience.
I think got both cases. Cause it depends like what type of shot you do, like what you forehand or you.
The idea, right? However you smack, right? You can never have slow to the top and then come down like that. And nobody hit on top.
I thought it's like when you reach the top, right, it's 0, then it slowly increase your speed. This will be faster.
But the time taken until you reach the top is fast, right?
If you reach faster than the one.
The time taken shorter. It's not about fast or slow because every instant the speed is different. The time taken for it to reach the top is lesser than the time taken for it to fall down. That's when you have air resistance. Okay?
Yeah, on the line.
Yep.